Hello there. This brief video is going to be all about orbital motion. So how we'll do this is we'll be looking at or recognize that gravitation provides the centripetal force for circular orbital motion. It is the key force which causes our planets to rotate around the sun. And this behavior of the solar system is summarized by something called Kepler's laws. Johannes Kepler came up with these rules to help explain the motion of the planets. So, first of Kepler's laws of planetary motion, not required by the IB, but interesting nevertheless. The orbit of each planet around the sun is an ellipse with the sun at one of the focuses. So you can see there we have a semi-major axis on one side and the fact that it is not a perfect circle, which is something which we observe. Kepler's second law of planetary motion, also not required by the IB, also fascinating nevertheless, is that if we look at the area, and in this case it's the area that it sweeps through in 30 days, we'll see that when it's close to the sun, and this is the perihelion, and when it's a long way away from the sun, this is the aphelion, we find out something quite interesting, and that's the fact that the area is the same. Okay, no matter where we have actually on the cycle, the area swept in 30-day periods are all equal. Third law of motion. This is the one with some mathematics involved, and this is where the IB like this one. So if we look at the square of the orbital period, we see it's proportional to the cube of the semi-major axis. Now, as long as we're only considering circular orbits, and this is actually how the IB simplify the world, then it becomes the radius of the orbit. So we can see that the average distance against the period squared gives us a proportionality, which is quite crucial. We see the relationship with just the period, but crucially it's the period squared which gives us that perfect proportionality. So if we have to derive the third law, we suppose a planet of mass m moves around with speed v in a circular radius r around the sun of mass m. And in this case, my little r squared is missing there, gravitational attraction of the sun is gmm over r squared, my floating r squared. This comes from Newton's law of universal gravitation. And if this is the centripetal force keeping the planet in orbit, then we recognize that this value must also be equal to the mv squared over r. This is from the centripetal equation, which we've worked out before. This can then be rearranged to show that gm over r, I'm sorry, I've got a floating r there, which shouldn't be, is equal to v squared. Now, if time of the planet to make one orbit is t, that means that the velocity is 2 pi r, which is obviously the distance around the orbit, divided by t, which is the period. If I square all these, I get lots of squared signs. But it also means that I can recognize that and simplify to the fact that gravitational constant times the mass equals 4 pi squared r to the cube divided by t squared. And so what we can come out from here is that r cubed divided by the period squared is equal to a constant. And this constant value is really, really crucial. So if r cubed over t squared is a constant, that is a big finding. That is our key features of orbital motion.